Welcome back to Weather Analysis with Mr. CB. Let's continue with this lesson number 4. So, let's talk about dry bulb temperature. Dry bulb temperature is actually just temperature as you already know it. Um, and the reason why it's going to be considered dry bulb um, is because, if we're talking about a bulb, these mercury thermometers that we used to use more, this end part is the bulb. And if it's dry, meaning it's not in contact with anything, it's going to just record the temperature as is, and it's not going to take into account moisture. But if we were to put that thing in a wet cloth, what would happen? It would smash into pieces, and then, I don't know. No, instead, we're going to get the wet bulb temperature. So what is this? How does this mean anything different? Well, what's going to happen when you have that wet cloth on there is, depending on how much moisture there is in the air surrounding that, um, energy is going to be taken from that apparatus, if you want to say, and we're going to get a different temperature that's recorded, and that's going to help us know um, a temperature that is dependent on how much moisture there is. So if the air surrounding that cloth surrounding the bulb, if that air surrounding it was dry, we're going to get a lower recorded wet bulb temperature, which is what that TW means, T subscript W. If it's humid, then it's going to be a higher recorded temperature and the reason why that is that there's going to be evaporation occurring, which in the last video, remember, we knew that that was a cooling process. So if when it's dry, there's going to be more evaporation that's going to happen. And since it's a cooling process, it's going to make there be a lower dry bulb or wet bulb temperature recorded. Still, it's always going to be lower than the real temperature. It's not possible for it to be above it, just like our dew point temperature. And if they're equal to each other, then our relative humidity is going to be 100%. That's the same thing, is that if our dew point temperature is going to be the same as our real temperature, also we'll know that there's saturation as well. Um, and in other words, this is going to be the temperature at which air could be cooled adiabatically through evaporation. It's going to be this blue line on the QT log P that we're going to talk about more soon. But remember, the red line is temperature, the green one is dew point, and then this blue one is going to be our wet bulb temperature. This blue line is going to help us know something different than what our green or red can tell us, which is that there can be fine lines between types of precipitation. So it matters to us a whole lot um, if it's going to be rain or if it's going to be freezing rain. Let's say we had a temperature that's like 33 to 35 degrees Fahrenheit. Well, the we should assume that the precipitation that's going to fall will be in liquid form, right? Because um, it would have to be below 32 degrees Fahrenheit for it to be not rain. But the thing is that there can be different layers as the rain falls, and there could be a dry layer. And remember, if that's going to happen, there's going to be evaporation. A dry layer will have evaporation, which is a cooling process. And remember, like I said, even though you might think, oh, well, evaporation, that sounds like a warming process to me, you we're not thinking about, okay, what's happening to a parcel. We're talking about what is it doing to the surrounding area. So if something is evaporating, it's going to cool the surrounding area. But um, we could even have snowfall that could just turn into gas form, which that's going to be sublimation if it's going from a solid to a gas, which is also a cooling process. So if you hit a dry layer in the atmosphere, then it's possible that something that was going to be snow is not going to be anymore. It might turn into just rain, or it could just sublimate. Um, we even have something called virga, which is going to be rain that can evaporate before it even reaches the surface because it hits dry layers. So have such things as dry storms sometimes where, oh, there is precipitation, but it hits a dry layer, so oh, it's just gone. Well, not gone, but it evaporates. So, as a review, if we have a larger difference between the actual temperature and the dew point temperature, we're going to have less moisture, so it's going to be drier. That's going to be more evaporation, sublimation, um, or sublimation, depending on the precipitation that occurs. So, is it going from a solid to a liquid, or solid to a gas, or liquid to a gas, like any of those that could happen. Um, so at this point, you might be wondering, it seems like that dew point temperature and wet bulb temperature are pretty similar. Well, in this video, I'm not going to explain the exact difference between them. They're not the same thing. They are somewhat similar and related, though. But just, you know, keep in mind what was talked about in the last video and this one. We are still going to use dew point temperature that's going to be still the measure that we're going to want to use to help us know how humid it might feel. A couple of other definitions that you're going to want to know. If we have hydrostatic balance, that's going to be a balance of the pressure gradient force with the force of gravity. Now, we're going to talk more about these forces a little bit later. And as far as density that we have in the atmosphere, it's important to know that it's going to decrease with height. Um, and that's because of gravity. So now let's talk about, we're gonna look, soon at these two maps, but let's look at this first. So lines of equal pressure, they are called isobars, in case you didn't know. Iso means same, so we could have isotherms as well, isohypes or isoheights. But isobars are going to be lines of equal pressure. So if we see that on the map, you can see these lines. So look right here. 998, that is going to be a slightly um, lower pressure because we use 1013 to say like if it's lower than that, then it's lower pressure and higher than that, high pressure. So this is going to be a lower pressure, but as you can see, we're going to say that anything that's on this line is also 998. You can trace that. It's a little bit hard to do. But you can see, yes, there you go. Then it's 998 again. Um, and anything inside that is going to be a lower pressure. So we have 997, then 996, 995, 994, and then all the way down to, oh, there's that low pressure system, 989. Pressure is or sorry, wind is always going to flow from high pressure to low pressure. So the wind right here would be going right to that. Um, and if these lines are closer together, then the wind is going to be stronger. So right here, they're not that close together. So it's like even right here, it's going to take longer. But here, look at those. That's kind of close together. It's going to be stronger winds right there. This map right here is going to be a surface level map, but we can also look at um, different other heights in the atmosphere. But The way that we're actually going to do it is by areas in the atmosphere of different pressure, not feet. And the reason why that is you'll see the second map. So what this one is showing is this is not a specific height in the atmosphere. This is a specific pressure. So everywhere on this map is going to be 300 millibar pressure everywhere on it. But the lines are ISO heights now. So that's the thing that makes this map a little bit tricky to understand at first, is because um, it's, we just see it in a 2D, but really what it's like, I guess I'll use this $10 bill that I, for some reason, had sitting there to show. So this one right here, it's all the same height, which is the surface. So on the surface, what's going on? We have different pressures. This one is not going to be the same height everywhere. It could be like this. This is the same pressure everywhere. So right here, you can see these numbers. The higher the number, the higher the height that it is. So this is a higher height here. This is lower height, 906, 972, 888. And this is going to be a ridge. So you can see, oh, it goes up. This 954. So this is really what we're looking at. It's going to be more like this. But everywhere on this map, it has the same pressure. So that's what we're saying. At what height in a certain location do we have 300 millibar pressure? And what is that going to mean? Um, if we have warmer air, uh, then basically you can see now we have a higher height. So because warmer air is able to hold more moisture, right? Um, so that's going to mean that the atmosphere is expanded at that point. And so if these black lines are isobars, um, you can see that where it's warmer, there's a higher height. So there's the same pressure, but it's at different heights. That's what we're having here. So you can see this is a ridge here. So we would expect there to be warmer than average temperatures there. But in other cases where there's a trough, lower. So that's just what I said. And so the equator is always going to have a higher 300 millibar height. So you can see the numbers are getting bigger down here as we're getting closer to the equator. You can see 960, 966, 972. Um, so we'll talk more about this later, but that's going to be something important to understand what this map is talking about. So this is not going to show us our high or low pressure systems. That's what's going to be this, which is at the surface. Here, it, all on the whole map is the same height, but different pressures that the map is showing. This is the same pressure, but different heights that the map is showing. So that was the 300 millibar one, and that's going to help us see jet streaks, troughs, and ridges. But there's other levels of the atmosphere that can show us uh, other levels in pressure that can show us different things. So 500 millibar could show us vorticity advection. Go up to 700, um, it's going to be vertical velocities. 850, we can see some temperature advection. Now keep in mind, as we're increasing in pressure, that's actually going to be at a lower height because pressure decreases with height. So actually each one of these is higher in the atmosphere, if that makes sense. But it's not going to all be the same exact height because though height and pressure are related, I just said As you go up, pressure decreases. Even though that's true, it's not going to be the exact same everywhere as this map shows. And sea level pressure is going to show us our lows and highs. Um, so now let's switch over and talk about some uh, atmospheric motion. So we can have horizontal and vertical motion. So for horizontal motion, let's first talk about the pressure gradient force, PGF. This is a force that happens because of pressure changes. Um, this is the pressure that makes there want to be motion horizontally. And what is that motion through? Wind. And I already said earlier in the video, we go from high pressure to low. So this is the motion. That's what this force is doing. It's saying, let's blow wind from high pressure to low pressure. Now, there's different things that can affect this force. How much of a pressure difference do we have? Is it a bigger pressure difference? Stronger force? We already looked at that on the map. I kind of said that. So if we are going from 1,000 millibars to 980, that's 20 millibar difference. So not as strong of a force than if it was 1,000 millibar to 950. That's a 50 millibar difference. So since it's a bigger difference in pressure, stronger force. Distance can also affect this force. If there is more distance between the two differing pressures or the isobars, bigger difference or a bigger distance between them means it's a weaker force. If they're closer together, if that change in pressure is closer together, then stronger force, stronger wind too. Another horizontal force that we have is the Coriolis force. Some people call it Coriolis effect also. Um, but this is going to be a deflection of wind. And so why would there be a deflection in wind? Why wouldn't the wind just blow straight? So you might think, okay, it's just going to blow exactly horizontal, but it's going to actually curve a little bit. And that's because the Earth is rotating. That makes sense, right? It wouldn't just be able to just go straight because it is not able to, it is going to deflect because the Earth, not only is it spinning, it's also curved anyways. Now, in the northern hemisphere, that deflection is to the right. So if I say to the right, that means if you're going directly north, if wind is blowing directly north, it's going to end up going east slightly. If it's going south, it's going to blow west. So let me try to draw that because it deflects to the right depending on which way you're thinking. So if um, this is for the Northern Hemisphere, which I'm American, and so that's really what we care about, or at least what I care about. So that means that it's going to go, oh, that's horrible. It's hard to draw with the mouse. So it's each thing that blows, or even if you're on a plane, it's going to go to the right a little bit. Even if you're going south, to the right a little bit. Even though that looks to the left, you're talking about from where you started. If you're pointing south, it's actually going to be to the west, but that's still to the right of where you were going. It's reversed in the southern hemisphere, but we don't really care about that. Like, at least I don't, because we're talking about American weather um, here. So that's not going to be relevant to us, what happens down there. This uh, means that this is why the planes are going to fly. If you're ever on a plane where you see um, the flight path, like sometimes they have that on their screens. You might see that it's not ever a straight line. Because if it was a straight line, you wouldn't end up in the place that you wanted to go. You have to actually curve to the left a little bit more to get to where you want to go. I went on a flight to from Los Angeles, California to Brisbane, Australia. Um, and it was very interesting seeing how that flight path looked, it was definitely not a direct line. For one thing, I went into a different hemisphere, so I say I don't care about the southern hemisphere. I've been there, but that's not what weather we're talking about. Things are a lot different down there for weather, so that's not what we're talking about. Apologies if you're in South America, Africa, or Australia, but I'm talking in Fahrenheit anyways, so maybe you wouldn't even, some of those places wouldn't want that anyways. But it is stronger the further you get from the equator, so for me, it's like it was very curved. It was more curved as I was first leaving Los Angeles, but as I got closer to the equator, it was like dun, 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 a little bit more straight. But then the Coriolis effect goes more as I went further south, as I was heading towards Australia. Um, and it's also going to be proportional to the wind speed. So what that means is if the wind is blowing faster, more Coriolis of force. So not going as fast, not as much Coriolis force. So there's also a centrifugal force, however you want to pronounce that word. This is going to be an outward force that acts upon an object. We're not going to talk about that much right now. Um, we also can have divergence and convergence. So divergence and convergence, they're also horizontal motion. So convergence is this. That's the second time my computer's almost died when I'm on a video or making a video. So I have to pause this because I won't be able to finish the video before I plug in thing. Okay, I have to sit at my Glory to Wome chair to plug this in. So listen to in Times New Roman, possibly. But anyways, so I was talking about convergence and divergence. So convergence is going to be a motion like this, divergence like this. So the thing about those two horizontal motions is that they can cause a vertical motion too. So what's going to happen when we have either of these? Well, if we have divergence, there's going to be a void, and air is going to either rise or sink after these motions, to fill that void that there is. And we're going to talk more about that later, though. All right, so let's continue on with this. Now let's talk about geostrophic wind and ageostrophic wind. So geostrophic wind, this is going to be wind that largely happens in our upper atmosphere. And it's going to be a wind that is going to have a balance between the pressure gradient's force and the Coriolis force. So as a reminder, what these forces are doing, the pressure gradient force is saying, go to a lower pressure now. So if we're at a higher pressure, we're looking around, lower pressure. It's saying wind blow in that direction. Coriolis is saying, well, too bad, go to the right some also. But eventually those are going to balance out. They're like, and they're going to be the exact same magnitude to the point that they're balanced. And now the wind is going to blow parallel um, to the height lines. So that's exactly what's going to happen now. It's going to blow parallel to these height lines. Um, so, oh, sorry about that. Um, the thing about that is that that's going to only be able to happen if there's no friction. So that's why it's mostly in the upper atmosphere. Ageostrophic wind, the prefix a usually means not, you know. And so now it's not balanced. Um, and this is what's going to happen at the surface. So now we have friction. There's going to be lots of reasons at the surface why we might have friction. But the thing that's going to happen, what does friction do? Friction is going to slow down that wind. So it runs into something like maybe a mountain or something like that. So it's like slows down. Well, we said before, Coriolis force is going to be proportional to the wind speed. So if the wind slows down now, well, the Coriolis effect isn't as strong. And now, not perfectly imbalanced anymore. Because even though the Coriolis effect or force got weakened, the pressure gradient force is like, I don't care. It's still just as strong as it was. So now, not exactly are we blowing parallel to the height lines, a little bit off now, okay? Um, so this is going to be a little bit easier to visualize. So check out this video representation of geostrophic wind and ageostrophic wind. So the pressure gradient force on its own would cause the wind flow to go straight from the high to the low pressure. So imagine that this train track is low pressure and I'm the wind walking to it. If you notice, the wind flow ended up exactly perpendicular to that isobar that you would consider that railroad track to be. Um, Not only will this happen from high to low pressure, but also high to low heights. On the other hand, if you had the Coriolis force only, this is a force that deflects wind to the right. So don't exactly know how it would be, but maybe not exactly like that. But what's really going to happen when we're at the upper levels of the atmosphere, since we have no friction, these two forces, they're going to end up in complete balance. And when that happens, instead, over time, the wind is going to blow parallel to these isobars and iso heights. If we're talking about more close to the surface and the planetary boundary layer, we will have friction, and the friction is going to slow down the wind. And since the Coriolis force is affected by the strength of the wind, that's going to weaken the Coriolis force. And now the Coriolis force is going to be weaker than the pressure gradient force. And now the wind's going to blow slightly diagonal, so not completely parallel to the isobars. Hi there, my name is Edgar Pigskin. Unfortunately, something happened when this video was being made, and I had to make this video myself. Sorry about that, Mr. CB.